Hey everyone, this is Lincoln. This is part 2 of the Noeput engine design overview. Today we're going to take a look at the injector and how it moves the propellants and coolant into and out of the engine. So we're going to start by looking at the propellants, why we chose them and how they flow through the injector. For this engine we chose nitrous oxide and ethylene, both of which are gaseous. The nice thing about nitrous oxide is that it can be decomposed through a catalyst into high temperature nitrogen and oxygen gas. This is helpful because that temperature, around 2000 degrees Fahrenheit, is well above the auto ignition temperature of ethylene, which is only between 700 and 800 degrees Fahrenheit. That means that the high temperature oxygen will automatically ignite and combust with the ethylene, eliminating the need for a complex ignition system, which would be difficult to integrate at this scale. We're now going to take a look at how each propellant flows through the injector and how we've designed the injector to optimize propellant mixing and enhance combustion. So on the left hand side is where the nitrous oxide enters the engine. It flows through this channel into this secondary chamber, which exists to distribute the gas into the catalyst bed, seen in orange. The catalyst bed is made up of 3 plates that have a series of holes drilled into them. This top plate has slots, and the bottom 2 plates have holes. The bottom 2 plates are also offset 90 degrees from each other so that no holes are directly over any other holes. This is to ensure the longest path length for each particle of gas, giving it the highest likelihood that it will undergo decomposition and turn into high temperature nitrogen gas and high temperature oxygen gas, which is what we want for complete combustion and efficiency of the engine. After exiting the catalyst bed, the nitrous oxide will enter this chamber here and exit through this orifice, which is a full ring, into the combustion chamber, where it will interact with the ethylene and combust. The ethylene enters on the right hand side through this port, through this channel, and out what's called a pintle injector. Pintle injector has 7 radial holes where the gas will enter the combustion chamber perpendicularly to the nitrous oxide, which will be coming down, whereas these will be going sideways. This ensures good mixing of the 2 propellants, which will ensure clean combustion. So after determining what kind of injector we wanted to use, we used simulations and calculations to determine the size of the injector. So for calculations, we looked at the chamber pressure, which is 12 bar, and the mass flow rate. To prevent backflow of the engine, in which hot combustion gases would go into the injector and potentially through the plumbing into our tanks, which would destroy the test stand, we have the injector at 15 bar, 3 bar higher than the combustion chamber. Using this pressure and the mass flow rate, we calculated the total area of the exit for each propellant. In the case of the ethylene, we divided that by 7 because there's 7 holes in this pintle. For the nitrous oxide, we had to find the area between 2 circles, a ring, and use that to get the outer radius. So as far as simulations, we took what's called the negative of this part, which is all of the space that the injector does not occupy. So all of the space that the gases would occupy. First we took a look at the oxidizer, as you can see here, put it into a program called SimScale, and ran it through a gas simulation. Using the simulation, we were able to determine that the particles of gas would indeed travel through the catalyst bed very slowly, ensuring complete catalyzation and decomposition. For the ethylene, we also plugged it in to SimScale and looked at this simulation here. So that's the propellant system as a whole. For a quick overview, on the left hand side we have the nitrous oxide enter, go through the catalyst bed here, decompose, and exit as a wall of gas surrounding the pintle. On the right hand side, the ethylene enters, goes through this channel, and exits through 7 holes in the pintle, colliding with that wall of nitrous oxide and combusting, powering the rocket. Now we'll move on to the coolant plumbing, which is water. So in the previous video we talked about multiple cooling methods, including regenerative cooling and film cooling. The water will be used for both. And as you can see here, it enters through two distinct channels and two distinct ports. On the left hand side, the water enters and goes into this channel here, exiting through the bottom through these 14 holes. These 14 holes correspond directly with the combustion chamber holes, flowing right into the regenerative cooling of the combustion, which is explained in the previous video. On the right hand side, some other water enters, going into this secondary channel, which distributes the water evenly into the primary channel, which is this inner channel right here, exiting through 7 holes. These 7 holes correspond with the holes in the pintle injector. As you can see here, this hole corresponds with this exit hole for the water. This is because the most combustion will happen around these 7 holes in the pintle. Thus, the hot spots in the engine will also correspond with those holes. So we want the most cooling to be where those hot spots are, so that the combustion chamber remains intact. Therefore, most of the water cooling exits through these holes and then spreads out from there, with weaker cooling in the spaces in between the holes. So now that we've gone over the propellant system and the coolant system, we're going to go over the structural system. So this injector also serves as the mounting point to the load cell, and then from the load cell to the test stand as a whole. So right here we have the load cell on top, which is an S-beam load cell, and the load cell mounting plate. If we take a look at just the load cell mounting plate, we can see that it has these holes cut out of it. This is to reduce weight and mainly material, because the more material we use, the more expensive this part will be, and the less efficient our engine will be as a whole. So in summary, today we went over the propellant system, which mainly uses this top piece here, the fuel and oxidizer injector, the water cooling system, which runs through the water injector down here, and the structural system, which consists of the load cell and the load cell mounting plate attached through the flange.